my name is Miguel Vasco, and I'm here to talk to you about my PhD project, which is entitled Multimodal Representation Learning for Robotic Cross-Modality Policy Transfer. And this is work I've been developing over the past 2 years under the supervision of Professor Francisco Melo and Professor Ana Paiva from Técnico, University of Lisbon. And while I was wondering how to approach this presentation, how to approach the topic of my project itself, I stumbled across this painting by George Morland entitled Blind Man's Buff, which depicts the well-known children's game. And while the topic of my project is not the game itself, it is in fact much related to the central figure of this painting, or, to be more precise, to the ability that allows a human to successfully play this game. Humans are equipped with a remarkable cognitive framework which allows them to take information provided by the environment in many different channels and process that information at modality-specific sensory organs such as the eyes and the ears. That processed information is then further refined in order to create multimodal representations of our environment, which allows us to understand the perceptions we are given. These very same representations also allows us to generate modality-specific data, such as image and sound, associated with that representation. And most remarkably, the same inference and generative processes are applied when the environment provides us with incomplete perceptions. And this is what we call cross-modality inference, the ability to generate a missing modality from the remaining available perceptions. And this ability is quite useful in some tasks. And here we would like to distinguish between two different types of tasks. On one hand, we have modality-specific tasks, which require information from a specific modality or subset of modalities for its execution. One example is sorting animals by their color. On the other hand, we have modality-independent tasks, which are tasks that can be completed using redundant information provided by many different modalities. One example of the later case is navigation tasks, and humans have remarkable performance when executing navigation tasks using visual information. Moreover, when that very same information is absent, humans are still able to execute the task, albeit with less performance, by considering information provided by our other senses, such as touch and sound. And this ability of cross-modality inference would be very interesting to extend to artificial agents, such as robots, right? Because robots, just like humans, are able to take information provided by the environment in many different channels, perhaps an even greater number than in the case of humans. However, when learning how to perform a task, robots usually limit themselves to visual information or to some sort of sensory fusion mechanism. And this limitation has consequences, because when we train a robot to perform a navigation task using visual information, it is able to do so. However, in the absence of that information, it fails to complete the task. And this leads us to the research question we try to address with our project, which is, how can artificial agents learn multimodal representations of their environment that allow the execution of modality-independent tasks? So we wish to take the insights from human multimodal representation learning and extend that to artificial agents. But that raises the question of how do humans learn these multimodal representations? And quite unsurprisingly, they do so in a myriad of ways. So considering supervised, unsupervised, and reinforcement learning mechanisms, which are computed in specific modules of the brain. We take the same approach with our work. So we wish to understand how artificial agents are able to learn these multimodal representations through supervised, unsupervised, and reinforcement learning mechanisms. So far we have addressed the first two mechanisms, and we wish to tackle reinforcement learning in future work. So regarding supervised learning, we were concerned with how can we learn rich multimodal representations of human actions in a household environment. We considered a scenario in which the environment itself is engineered with a number of sensors which are able to give us information regarding not only the motion of the human during the action, but also some sort of contextual information regarding the objects that the human is using and the location where the action is being performed. From the data provided by a demonstration of an action, we are able to create a new multimodal representation which we call the motion prototype. And from several demonstrations of the same action class, we are able to generalize that into the representation which we call motion concept, which is the generalized representation of an action class. Furthermore, we have also developed the online motion concept learning algorithm, which is an algorithm able to learn new motion concepts from demonstration data provided by a human, but also to recognize a demonstration as an example of a previously learned motion concept. We have evaluated our algorithm in two different tasks. The first one was an offline one-shot recognition task in which we shown that our algorithm OMCL is able to outperform baseline models. The second task, it was an online learning and recognition task in which we shown that OMCL is able to distinguish between the demonstration of a new motion concept and a demonstration of an example of a previously learned motion concept with high performance. So regarding the unsupervised learning of multimodal representations, we consider the domain of Atari games. And there's been a lot of recent development on new and improved deep reinforcement learning algorithms to learn to play these games. Yet, the majority of them assumes that the agent is always provided with image information at test time. In our work, we are interested in scenarios in which that does not happen. The agent does learn how to play the game from image inputs, however, sometimes is not able to get that information from the environment. Our approach allows an agent to transfer that very same policy, now considering sound inputs, and play the game without requiring further training or fine-tuning of that policy to the new modality. In a sense, it allows agents to play games in the dark. Our approach has two different steps. On the first one, we have the unsupervised learning of a multimodal representation of the game environment, considering the images and the sounds provided by the games, and we use multimodal generative models. On the second stage, and considering images as input, we then learn how to play the game, considering the multimodal representations as the states of the environment. We show in our work that an agent, when provided at test time with sound inputs, is also able to play the game with minimum performance loss. If you are interested in this work, please go check Rui Silva's presentation at AAMAS 2020. Finally, for future work, we wish to tackle how reinforcement learning can help us further refine the representations we learn using unsupervised learning methods. For example, when we were learning how to play Atari games and we were learning a representation of the game environment, we found out that it does not take into account the features that are fundamental to actually play the game. For example, in the game of Pong, that would be the paddles and the ball. We wish to understand how attention mechanisms can help further refine the representations that we get. The second stage of our future work concerns the extension of all the work we have done with RL agents now to a real-life robotic platform in a navigation task. So we hope that at the end of this project, we are able to further give insights to how artificial agents learn these multimodal representations and their role in the execution of modality-independent tasks. Thank you very much for listening.